Welcome! Today, we'll be exploring problem number 474, ones and zeros. This is an interesting problem that challenges our understanding of dynamic programming and combinatorial optimization. Let's dive into the problem details and explore some effective solutions. In this problem, you are given an array of binary strings called SCRS and two integers, m and n. The goal is to find the largest subset of these binary strings such that the total number of zeros and ones in the subset does not exceed the given limits of m and n, respectively. Each string contributes to the count of zeros and ones, and the overall counts across the subset must stay within these constraints. For the input format, STRS is a list of binary strings that contain only the characters 0 and 1. The integers m and n represent the maximum number of zeros and ones allowed in the subset. The output will be an integer that represents the size of the largest subset that satisfies these constraints. Let's explore some examples to better understand the problem. In the first example, the input is STRS equal to 10,0001, 111,001, 1, 0, with m set to 5 and n set to 3. The output is 4. This is because the subset 10,0001, 1, 0 is valid. When we count the zeros and ones in this subset, we find that it contains exactly 5 zeros and 3 ones, which matches the given limits. This is the largest possible subset that satisfies the constraints. Notice that the string 111,001 cannot be included because it would push the count of ones beyond the limit of 3. By excluding it, we ensure the subset remains valid while maximizing its size. In the second example, the input SCRS is 10, 0, 1, with m equal to 1 and n also equal to 1. The output in this case is 2. Here, the valid subset is 10, 1, which contains 1, 0 and 1, 1, staying within the given limits. Although the string 0 could fit within the limit for zeros, adding it would exceed the limit for ones, so it is excluded. Moving on to the constraints, the array STRS can have a length of up to 600. And individual strings within SCRS can be as long as 100 characters. All strings consist exclusively of the characters 0 and 1. The values of m and n range from 0 to 100. Additionally, some edge cases to consider include scenarios where STRS contains only one string, or when m or n is 0, meaning only strings with no zeros or ones, respectively, can be included. If no valid subsets can be formed, the result will be 0. To solve this problem, we first consider two main approaches. The brute force approach is the most straightforward. Here, we generate all possible subsets of the input array SCRS and check each subset to see if it satisfies the constraints of having at most m zeros and n ones. From the valid subsets, we select the one with the largest size. While this approach is intuitive, it is computationally expensive because generating all subsets has a time complexity of 2 to the power of k, where k is the length of the STRS array. Additionally, for every subset, we need to count the zeros and ones, which makes this method impractical for larger inputs. Instead, we turn to the dynamic programming approach. This method draws inspiration from the 0/1 knapsack problem. In this analogy, each binary string is treated as an item with weights corresponding to the number of zeros and ones it contains. The objective is to maximize the number of strings we can include in our subset without exceeding the given constraints on zeros and ones. This forms the foundation of the solution we will use. Now, let's break down the dynamic programming approach step by step. First, we observe that each string in the input array contributes a specific number of zeros and ones. The constraints m and n act as the capacity limits for these quantities, similar to the capacity in a knapsack problem. Using this, we can define a two-dimensional dp table. In this table, dp, I, j, represents the maximum number of strings we can include in a subset when we have at most I zeros and j ones available. To build this table, we calculate the contribution of each string by determining the counts of zeros and ones it contains, referred to as count 0 and count 1. The dp table is updated in reverse order, starting from the maximum values of m and n and moving down to the respective counts of the current string. This reverse update ensures that we do not overwrite results from the current iteration. The transition formula is simple. For each cell, the value is the maximum between its current value and the result of including the current string, which is 1 plus dp, I count 0, j count 1. Finally, the base case is straightforward. When both the 0 and 1 capacity are 0, no strings can be included, so dp 0, 0 equals 0. Ultimately, the solution lies in the value stored at dp m n, which gives the maximum number of strings that can be included while respecting the constraints. The time complexity of this approach is O, k*m*n, where k is the number of strings in the input array, and m and n are the constraints. This is significantly more efficient than the brute force approach, making it suitable for larger inputs. The space complexity is O, m*n, as the DP table requires a 2D array of this size to store intermediate results. Dynamic programming is the preferred solution for this problem because it balances efficiency and clarity. By leveraging the knapsack analogy, the transitions become intuitive, and the approach ensures correctness and optimality. While the space complexity is notable, it is manageable within typical constraints like m, n equals 100, making this solution practical for competitive programming scenarios. While the dynamic programming approach is robust, it is worth considering alternatives. A greedy approach, for example, might prioritize strings that provide the highest contribution relative to their resource usage, that is, the ratio of strings added to zeros and ones consumed. However, this does not guarantee an optimal solution, as there is no clear heuristic to maximize the subset size without evaluating all possibilities. Another option is to optimize the space complexity of the current DP solution. By using a 1D array instead of a 2D table, we can reduce the space complexity to O, m*n. However, this introduces additional complexity in the implementation, as we must carefully manage updates to the array to avoid overwriting values prematurely. Ultimately, the dynamic programming approach remains the best choice due to its balance of clarity, efficiency, and scalability. It effectively uses the knapsack analogy to ensure both correctness and optimality, making it the most reliable solution for this problem. The problem we're solving involves selecting a subset of strings from the array strs such that the subset adheres to specific constraints. Each string is composed only of the characters 0 and 1, and we need to ensure that the total number of zeros in the subset does not exceed m, and the total number of ones does not exceed n. The objective is to maximize the size of this subset while respecting these constraints. To approach this, we use dynamic programming. The state of our solution is represented by a DP table, where dp I, j signifies the maximum number of strings that can be included in a subset when we have I0s and J1s available to use. The table has dimensions m+1 each x, n+1, to account for all possible combinations of available zeros and ones. Initially, we set all entries in the DP table to 0, as the base case represents no strings being selected yet. Now, we consider processing each string in the array strs. For any given string, we calculate the number of zeros, denoted count_0, and the number of ones, denoted count_1, that it contains. To update the DP table, we iterate in reverse order, starting from m down to count_0 for the rows, and from n down to count_1 for the columns. This reverse iteration ensures that the updates from the current string do not overwrite states from the same iteration. For each state, I, j, in the DP table, we have two choices: either exclude the current string, in which case the value remains dp I, j, or include the string, which adds 1 to the maximum size of the subset achievable with the remaining resources. This is represented by dp I count_0, j count_1, plus 1. We take the maximum of these two values to ensure we capture the optimal solution. Once all strings have been processed, the value stored in dp m n will give us the maximum size of the subset that meets the constraints. This dynamic programming approach relies on a few key insights. First, the DP table captures every possible state of the problem, ensuring that no potential subsets are overlooked while adhering to the constraints. The use of reverse iteration is critical because it prevents overwriting results from the current iteration, which could otherwise corrupt the DP transitions. This method is also highly efficient compared to a brute force approach that would involve generating all possible subsets. Instead, we achieve the solution in O, k*m*n, time, where k is the number of strings in strs. The data structures used include the 2D DP table dp, which has dimensions m+1 each x, n+1, to store intermediate results for all states. Additionally, auxiliary variables like count_0 and count_1 are used to streamline the calculation for each string. In terms of complexity, the time complexity is driven by the number of strings and the size of the DP table, while the space complexity is O(m*n) for storing the table. Finally, let's consider some edge cases that the algorithm must handle. First, there may be strings that contain number zeros or ones, such as an empty string. These strings do not contribute to the constraints and are effectively ignored. Second, strings that have a number of zeros greater than m or a number of ones greater than n are automatically excluded because they exceed the available resources. Lastly, if the input array strs is empty, then no subset can be formed, and the result is simply 0. These cases ensure the robustness of the solution, handling both typical and boundary scenarios effectively. This solution tackles LeetCode problem 474 using dynamic programming to solve the subset selection problem with constraints on zeros and ones. Here's how the code works. 1. Initialize the DP table. The DP table is a 2D list with dimensions m+1 affix n+1, where dp I, j represents the maximum size of a subset that can be formed using at most I zeros and j ones. Initially, all entries are set to 0 since no strings have been considered yet. 2. Process each string. The algorithm iterates over each string in the input list strs. For each string, it calculates the count of zeros, count 0, and ones, count 1, using Python's count method. 3. Update the DP table. The DP table is updated in reverse order, starting from m down to count 0 4 zeros, and n down to count 1 4 ones. This reverse traversal ensures that updates do not overwrite values that are yet to be considered in the current iteration. The key update formula is dp I, j equals max dp I, j dp I count 0, j count 1, plus 1. This formula determines whether including the current string results in a larger subset size compared to excluding it. For final result, after processing all strings, the value at dp m n contains the maximum size of the subset that can be formed with at most m zeros and n ones. This approach efficiently handles the constraints by leveraging dynamic programming, avoiding the need for exponential subset enumeration. The time complexity is O(len) strs *m*n, where len strs is the number of strings in the input list. The space complexity is O(m*n) due to the DP table. Here, we start by importing the necessary utilities and defining our solution class. The main method, findMaxForm, takes 3 arguments, an array of binary strings strs, and integers m and n representing the maximum number of zeros and ones allowed. We initialize a 2D dynamic programming table dp of size, m+1 affix n+1, where each cell represents the maximum number of strings that can be formed with a specific count of zeros and ones. Initially, all cells are set to 0. Next, we loop through each string in the input array. For each string, we count the number of zeros and ones it contains. This is done using a simple loop over the characters of the string, incrementing count 0 4 zeros and count 1 4 ones. Once we have the counts, we traverse the DP table in reverse order. This reverse traversal ensures that we do not overwrite values from the current iteration that are still needed for subsequent calculations. For every cell, we decide whether to include the current string by comparing the existing value with the value obtained by including the string. If including the string produces a larger subset, we update the DP cell accordingly. Finally, after processing all strings, the solution lies in the cell dp m n, which represents the maximum number of strings that can be formed using up to m zeros and n ones. This value is then returned as the result. The logic ensures that we consider every possible combination of strings while respecting the constraints on the number of zeros and ones, and the use of dynamic programming ensures the solution is efficient. This completes our implementation of the problem in Java. The problem ones and zeros provides us with a list of binary strings, and our goal is to determine the maximum subset of these strings that can be formed using at most m zeros and n ones. Each string in the list is composed solely of the characters 0 and 1. To solve this, we employ a dynamic programming approach. Specifically, we define a DP table dp I, j, where dp I, j represents the maximum size of a subset that can be formed with up to I zeros and j ones. This allows us to systematically evaluate the constraints while building the solution. For example, consider the input strs equals 10 0001 111001 10, along with m equals 5 and n equals 3. In the first step, we initialize the DP table. Since we can use up to m0s and n1s, the table will have dimensions m plus 1 equals n plus 1, and will initially be filled with zeros, indicating that no subset has been formed yet. The table at this stage looks like this. DP equals 0, 0, 0, 0. 0, 0, 0, 0. 0, 0, 0, 0. 0, 0, 0, 0. 0, 0, 0, 0. 0, 0, 0, 0. Having established the table, we can now move on to processing the strings one by one and updating the DP table accordingly. Now we begin processing each string from the input list, updating the DP table as we go. Starting with the string 10, we observe that it contains 1 0 and 1 1. This means we need to consider all subsets that could include this string, ensuring we don't exceed the constraints of m0s and n1s. To achieve this, we update the DP table in reverse order, iterating I from m down to the number of zeros in the string, and j from n down to the number of ones. For instance, when processing 10, we calculate values such as dp 5, 3 equals max, dp 5, 3, dp 4, 2 plus 1, resulting in an updated value of 1. Similarly, we update dp 4, 3, dp 3, 2, and even dp 1, 1, along with other relevant entries. Each of these updates reflects the inclusion of the string 10 in the subset, increasing the maximum subset size while adhering to the constraints. This process is repeated for every string in the input list, systematically building up the DP table to ultimately determine the largest possible subset size that meets the given criteria. To analyze the time complexity of this algorithm, we can break it down into three main steps. First, we initialize the DP table, which is a 2D array of size, m plus 1, by n plus 1. Here, m is the maximum number of zeros allowed, and n is the maximum number of ones allowed. Filling this table with initial values requires m*n time. Next, we process each string in the input array, strs. For every string, we count the number of zeros and ones. If the average length of a string is L_average and there are k strings in total, this counting step contributes k*L_average time overall. Finally, we update the DP table. For each string, we iterate backward through the ranges from m to the number of zeros in the string and from n to the number of ones. Each string contributes m*n updates, so with k strings, this step totals k*m*n. This means the most time-consuming part is the DP update step, which becomes the dominant contributor to the time complexity. When we combine all the steps, the initialization of the DP table takes m*n, the counting of zeros and ones contributes k*L_average, and the DP table updates require k*m*n. Since the DP update step dominates, the overall time complexity of the algorithm is k*m*n. Now, let's consider the space complexity. The algorithm uses a 2D DP table of size, m plus 1, by n plus 1, which requires m*n space. For string processing, we only compute simple integer counters like the number of zeros and ones, which use 1 space per string. Additionally, storing the input array strs takes k*L_average space, where k is the number of strings and L_average is their average length. These are the key contributors to space usage in this algorithm. When we account for all components, the total space complexity is m*n for the DP table and k*L_average for the input storage. Thus, the combined space complexity becomes m*n plus k*L_average. Now, let's compare this dynamic programming approach to a brute force method. In a naive approach, we could generate all possible subsets of the input strings and check if each subset satisfies the constraints of having at most m0s and n1s. With k strings, there would be 2 to the power of k subsets to evaluate. Additionally, checking each subset could require up to k*L_average time, making the overall time complexity 2*k*L_average. This is exponentially worse than the dynamic programming solution. For space, the brute force approach would be dominated by the recursion stack or the subset generation, which could reach k. Clearly, the dynamic programming solution is far more efficient. When analyzing the algorithm's behavior under different scenarios, we see that the time complexity remains O, k m*n, regardless of the case, but the constants vary. In the best case, where m and n are small, the DP table is smaller, which reduces the overhead. For the average case, we assume typical values for m, n, and the number of strings k, and the complexity remains O, k m*n. In the worst case, both m and n are large, requiring the full DP table, and k is also large, leading to maximum processing overhead. Finally, from a mathematical perspective, the algorithm iterates over each string and updates the DP table, which has a size of O, m*n. Since each update is done in constant time, the complexity scales linearly with k and quadratically with m and n. For space, the DP table and input storage dominate, leading to a total complexity of O, m*n plus k*l_average, as discussed earlier. When working on this problem, one common mistake is not accounting for the constraints properly. For example, failing to count the number of zeros and ones in each string accurately can lead to incorrect results. It's crucial to validate your implementation with corner cases, such as strings that consist entirely of zeros or entirely of ones. These edge cases often expose hidden bugs that might otherwise cause your solution to fail during interviews. Another frequent issue is relying on an inefficient brute force approach. Generating all possible subsets of the input array can be computationally expensive, especially as the input size grows. This method has a time complexity of O, 2 to the power of k, where k is the length of the array, and it's unlikely to meet performance requirements for larger inputs. Lastly, incorrect handling of the dynamic programming state can derail your solution. In this problem, the state is typically represented as dp, I, j, where I is the number of zeros and j is the number of ones. Without a clear understanding of how to transition between states, you may end up with incorrect results, as state transitions form the foundation of any DP-based approach. Now, another potential pitfall in solving this problem is not considering the lengths of the strings. Longer strings inherently consume more zeros and ones, so it's important to account for this in your solution. At times, prioritizing shorter strings can lead to a more optimal subset. Overlooking such nuances can result in suboptimal results that fail to meet the problem's requirements. Additionally, edge cases like an empty strs array or constraints where m equals 0 or n equals 0 are often neglected. Such scenarios need explicit testing to avoid runtime errors or incorrect outputs during interviews. On the positive side, this problem offers valuable insights for interviews. Recognizing patterns such as at most X of this resource is a key skill because these often lend themselves to dynamic programming or greedy algorithms. This recognition can save you time by steering you away from brute force solutions early on. Optimization is another focus point for interviewers, so demonstrating your ability to transition from a brute force approach to an optimized dynamic programming solution is critical. Make sure to clarify constraints and edge cases at the beginning of the problem to ensure your solution is aligned, and communicate any trade-offs if you start with a less efficient approach before refining it. This problem also shares similarities with several other dynamic programming problems, which can help you identify patterns and connections. For instance, LeetCode 416, partition equals subset sum, is a knapsack-style problem where the goal is to divide an array into two subsets with equal sums. The problem at hand, LeetCode 474, focuses on maximizing the subset size under specific constraints. LeetCode 322, coin change, involves resource allocation and has constraints similar to a knapsack problem. Finally, LeetCode 139, word break, is another DP-based problem where decisions are made step by step based on constraints. Each of these problems reinforces techniques like state management and constraint handling. When considering alternative approaches, brute force is the simplest to implement but computationally expensive, with a time complexity of O, 2 to the power of k. It's generally only suitable for small input sizes or as an initial step to understand the problem. A dynamic programming approach, particularly a knapsack-style solution, is far more efficient for larger inputs, with a time complexity of O, m*n*k. However, it does require careful attention to state transitions and management, making it the preferred method for interviews due to its scalability. Finally, a greedy approach can sometimes be considered for specific variations of the problem. While it may be simpler to implement, it doesn't guarantee optimal solutions in general and is less reliable for problems with stricter constraints. Greedy methods are typically more suitable for simpler problem variants or cases where the constraints are relaxed, as they focus on making locally optimal choices without considering the global picture. Ultimately, understanding the strengths and weaknesses of the brute force, dynamic programming, and greedy approaches will help you choose the most appropriate solution for the given problem constraints and input size. Great job! We tackled problem number 474, ones and zeros, and explored how dynamic programming can help solve it efficiently. Remember the importance of understanding constraints and breaking problems into smaller subproblems. Thanks for watching, and don't forget to subscribe for more engaging coding tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!